Hello. It's an honor today to present or to welcome Ingrid Wilke here for the talk during her stay for 2 months at KIT. So Ingrid Wilke studied at State University of New York in Albany and at Universität Würzburg, and then finished her PhD in ETH Zurich. And then she did several postdoc stations, for example, at Lawrence Berkeley National Lab in the US and at the Tokyo University in Japan. And then she went to a University of Hamburg and finished her PhD there. As you said, in 2002, she joined the Rensselaer Polytechnic Institute as a professor in the Department of Physics, Applied Physics, and Astronomy. She received several fellowships, grants, and honors, which I won't listen here in detail. But she had very important contributions in the development of terahertz wave detectors, radiation sources, and system technologies, and the understanding of electronic material properties in the terahertz regime. During her stay in Hamburg, which is of particular importance for the audience here, she was a pioneer in electro-optic relativistic electron beam diagnostics at linear accelerators in that case. So she was the first to demonstrate single-shot EO electron bunch length measurements at that time at the Felix free-electron laser. So this is the connection between IBPT and Ingrid Wilke's background, maybe. I met Ingrid personally at several conferences when I was still in the terahertz science field. And then when I came here at IBPT in 2019, she invited me to give a talk at the German Conference on Women in Physics. And after we started a collaboration, and she will now give a talk with this new electro-optic sensors based on thin film lithium niobate. So I look back to the last weeks with successful measurements, and I'm trying to listen to your talk.
Thank you very much for the introduction and very warm welcome. So I would like to thank particularly Gudrun Nivus for the successful nomination as an International Excellent Fellow, also to Lena Pfeiffer and her office, who really makes it a pleasure for the fellows to be here with all the administrative work in the background. And I would also like to thank Anke Susanne Müller for hosting me in the Institute and making this wonderful research infrastructure available. And I have interacted with a lot of the people here in the audience from the IBPT, and I can only say it was a pleasure so far. Also, thank you for this. Okay, then let's start with the presentation. This is first, before I start, I would like to introduce my research team at Rensselaer Polytechnic Institute. The students John Rawlinson and Jackson Monahan have contributed to the research, and also in the early days my colleague Mona Heller. Then we are in a close partnership or in a team with Payam Rabiai and Seyfola Toroki at Art of Technologies. This is a very small company. They both own it, but they have over the last 20 years really made original contributions to the development of thin film lithium niobate materials. Then I have I collaborate with accelerator laboratories. I have worked with George Hein at the Linear Accelerator Research Division at Oak Ridge National Laboratory. We will see later during the talk. They also have a high-intensity time domain terahertz wave radiation source, which we used for sensor testing. And now I am here collaborating at the IBPT, basically on a daily basis in the laboratory with Gudrun Nivus. But the successful experiments have also received report through Johannes Steinmann, but he helped us with the sampling oscilloscopes and also with data acquisition. Also, Stefan Funkner contributed to experimental control and full day of measurements, and Marvin Noll patiently printed again and again improved laser printed improved sample holders. Okay, in my presentation, I want in the beginning also, we have some people in the audience who bring not special expertise to the talk. So I want to give a kind of general introduction of what we are measuring, what approach we are using, and why it is important. And then I will talk about the photonic integrated electro-optic and field sensor, the design of the sensor, the fabrication, and the performance validation we have been and are currently performed. If we have an electron, then an electron has an electric field, and if the electron is at rest, then the electric field is radially outward, as indicated here in this cartoon. And if the electron now starts moving, and it moves very fast, like at speeds close to the speed of light, the electric field is no longer radially, but it becomes more and more transverse versus the direction of propagation of the electron. And what we try to do when we talk about electro-optic electron beam diagnostics, we try to measure here the electric field of those electrons which are moving at very, very high speeds. This is the measurement problem. And we do this by using the linear electro-optic effect, which is also called the Pockels effect. So if I have an electro-optical crystal and I apply an electric field to the crystal, and then if I pass a linear polarized light, which is generally laser light, through the crystal, then the polarization of the laser light is modified, and the change in polarization of the laser light is proportional here to the strength and the direction of the electric field. So if we bring such a crystal in the vicinity of an electron, then the electric field of the electron will modify here the properties of the material, and then by we were probing here this change with the laser. Okay, this is an early example of electro-optic beam diagnostics at accelerators. I did this the actual experiment was almost 25 years ago at the University of Hamburg when I was working on my habilitation in experimental physics. And the experiment were performed at the Felix free-electron laser in the Netherlands. So the free-electron laser is driven here by a linear accelerated electron beam, and then we put a zinc telluride bulk crystal in the beam pipe in the vicinity of the electron beam. And now if the electron beam travels past the crystal, it changes here the optical properties of the material, and those changes are here probed with the laser beam. The laser beam has a linear polarization, and then afterwards the change in linear polarization is here analyzed using an analyzer. And so this is then how the basic principle of the diagnostics. Here in this case, we did single shot measurements. So the femtosecond laser pulses, they were stretched with an optical stretcher, so that the laser pulse was slightly longer than the electron bunch. And then basically, if we capture the single laser pulses, we have really the full information on the electron bunch length. And this is here the example. This where with the peak is the measurement with the electron beam present, and this is the signal. This is here the reference measurement. And then if we subtract those two spectra from each other, we get the electron bunch length. So at that time, the pulses at the Felix, they were like 6, the full length 6 femtosecond, and full width half maximum with somewhere, I don't know, maybe 2 to 3. And I think the bunch charge was in the order of 100 picocoulomb. Okay, so what are now the new perspectives? If we look at the state of the art, it is done with bulk optical components, also for electron beam diagnostic, bulk zinc telluride crystals are used, or bulk gallium phosphide crystals are used. And then also the optics, which is needed to analyze the information, are bulk optical components like half-wave plates, quarter-wave plates like prisms. This is one standard configuration, or if it's a polarizer analyzer combination, it's also about bulk components. And now what we decided to do is to now basically put all this on a small 1 by 1 millimeter chip, and all those functionalities are now supported by one photonic integrated circuit. So next I talk about the design of the sensor. Sensor itself is a Mach 10 interferometer type electro-optical modulator, and basically all the components here of the device are basic building blocks from integrated photonics, which were primarily developed like for communication purposes. So we have here that this is the input of the device. This is where the laser probe pulse enters the device. Then we have here a 1x2 multimode interference coupler. This is a waveguide structure which acts as a power splitter. So here the laser light which enters is divided in two beams with 50-50 power division. Then we have here, these are the arms of the interferometer. And then we have here a 2x2 multimode coupler, which divides the laser light which comes out of the MZE here into separate channels. Then the sensor operates in the following way. Also the optical laser light and the terahertz laser light, they have to travel in the same direction, and the electric field of the linear polarized laser light has to be parallel to the two arms of the Mach 10 interferometer. So this is the top view, and this is now the cross-sectional view. We have here approximately 600 nanometer of thin film lithium niobate on an insulating substrate, fused silica, which is 500 micrometer thick. And another property of the lithium niobate, which is now exploited for device operation, is that it is a ferroelectric, and it is a ferroelectric where the polarization is stable at room temperature. So I will later show how it's done during fabrication. So if we have here the two arms of the interferometer, then the lithium niobate is polarized in opposite direction here under the waveguide. This is the device. These are technical details. We have like X-cut lithium niobate, and the polarization of the optical mode is parallel here to the extraordinary axis of the material. Then we see here, this kind of indicates how we operate it. This is again a kind of top view schematic of the chip. The laser light is coupled from the fibers to the device using grating couplers. And here the cylinder is a kind of indicating the terahertz radiation beam. So we see here, if the terahertz radiation travels here in this direction, then the electric field here is parallel to the arms. This is a picture of the packaged device. Also there is like approximately 20 millimeter long plastic housing, and then the chip is here at the tip of the housing, and it is perpendicular here to the length of the housing. If we look at the device, then the phase change, which is induced by the terahertz electric field, is proportional here to the amplitude of the terahertz electric field, to the length of the arms of the MZI. So this is this distance, the electro-optical coefficient of the lithium niobate, the index of refraction of the lithium niobate for the optical light. And then we have here a transfer function. This is basically the bandwidth of the modulator. And there are different parameters which determine the bandwidth of the modulator. And here in this diagram, we see how the length of the modulator arms influence the bandwidth. So we see the shorter the structure is, the larger the bandwidth. And then if the arms become longer, then the bandwidth reduces, but then the device becomes more sensitive, because here the phase change is also proportional to the length of the device. Then we also see that the transfer function here, this is the transfer function, is the modulator response is frequency dependent, and this frequency dependent is determined by the difference between the index of refraction for the terahertz wave and the optical wave, because they determine the speed at which the two waves are traveling. And if they are matched, if they have the same value, we basically have an infinite bandwidth. So we can detect the frequencies over a large range, and the more they differ, the smaller the bandwidth will be. This is a diagram which shows how the modulator response depends on the materials used. So we have here the substrate. So we see here the modulator response for a fused silica substrate versus the modulator response for a crystal quartz substrate. And what is now happening here, we see that the thickness in the two layers is very large. It's almost a factor of 1,000. Also, the fused silica has a 500 micrometer thickness. The thin film lithium niobate is 600 nanometers. So the ratio is roughly in thickness 1,000. And since the silica is much thicker than the thin film lithium niobate, the terahertz wave travels in the substrate. And so what matters for the index of refraction for the terahertz wave, it is actually the index of refraction in fused silica, which is like a 1.95. And for the optical wave, what matters is here the material and also the waveguide geometry. Also it is possible here, through the dimensions of the waveguides, like the thickness here, the height of the waveguide, also to engineer the index of refraction for the optical wave. And therefore it is then possible basically here to minimize the mismatch of the two indices of refraction, and as a result here to increase the bandwidth of the device. If you look at the bulk lithium niobate crystals, which have a large electro-optical coefficient, but they have a very strong mismatch here in the indices of refraction for terahertz waves and for optical waves. And therefore, bulk lithium niobate modulators, which are a product which are used in optical communication networks, they have a bandwidth which is limited basically to 100 gigahertz. As I think most of the commercial lithium niobate modulators from bulk crystals, they operate up to 30 gigahertz for communication networks. And I know, at least from the US, that there are special military applications, and for this purpose it is still possible to fabricate modulators with bulk crystals which operate up to maybe 110 gigahertz, but this is basically the limit because of the larger mismatch. But as I said, we look at the terahertz wave traveling in diffuse silica. The index of refraction is 1.95 at terahertz frequencies, and the index of refraction for the device we are currently devices we are currently investigating is 2.5. So we see here in the thin film lithium niobate module data, the velocity mismatch is reduced by a factor of 10, and as a result, also the bandwidth is much enlarged. The thin film lithium niobate is fabricated really from bulk crystals. So it is possible bulk crystals can be grown with really high quality, really high optical quality single crystals. And then the way the thin layers are fabricated is that the bulk crystal is ion implanted. So at the specified depths, which usually then corresponds to the thickness of the thin film layer, the crystalline structure is disturbed by ion implantation. Then the ion implanted crystal is wafer bonded to the substrate, like for example the fused silica, and then the bonded structure is reduced. And then as a result of thermal expansion, here the crystal breaks at the ion implanted layer. This is also then called crystal ion slicing process, and this basically just pops off. And then we have here the thin film lithium niobate on the insulating substrate like the fused silica. Then for the poling of the lithium niobate, two metal electrodes are applied to the thin film, and then then there is an electrical voltage applied, and here in one area the polarization is reversed, and then in the next step, using electron beam lithography, here the waveguides are defined, and the other structure like the multimode interference couplers and the gratings for coupling, and then the device is ready, and then there's a passivation layer on top. Okay, now we come to the sensor performance validation in the terahertz frequency band. Initial validation was performed at 100 kilohertz, simply in a parallel plate capacitor. And then we started to work on the terahertz. So this is an experiment where I worked with George Heim at Oak Ridge National Laboratory. They have also a high intensity terahertz time domain radiation source. They are also in this sense interested in the source to use the terahertz field for the acceleration of charged particles in of accelerator development. And there we were using a pump broke the geometry, so the laser beam was split in a pump beam, which did generate terahertz radiation pulses from organic crystals. And then the probe beam was coupled into in the fiber, which connected here to the sensor. And then the two output fibers of the sensors went to a balanced photodetector, and then the signal was recorded by an oscilloscope. And we were working here in a pump probe geometry at 15 nanometer. There was an optical parametric amplifier available, which is pumped by a Titan Sapphire regenerative amplifier. So there was ample spectrum and ample laser power to prepare the pump and the probe beam at 50 nanometer. The pulse duration was 40 femtosecond, and the repetition rate 1 kilohertz. This was a measurement where the signal acquisition was done in a single laser pulse mode. So the signal we got was really the signal from a single laser pulse. this is the result. So we see here the time, an example of a time domain transients, which we measured with the sensor using the system I just described. So we see the characteristic temporal shape of the pulse, like we would expect it if we use femtosecond laser pulses and organic crystals. And the black trace here, so this is a kind of a zoom of this area. This represents the average of 16, the signal of 16 individual laser pulses, which were recorded. So we see here in gray, this is the scattering of those 16 individual laser pulses. This is an experiment where the terahertz electric field strength is on the order of like a megavolt per meter. So we have a really strong terahertz field, and the sensor has sufficient sensitivity basically to start to generate a signal based on 60 individual laser pulses. I mean, this was an experiment. If I go back, we also had limited time to do it, so we just, in this sense, the terahertz field was not focused on the device. There was, after the emitter, there was a high-density polyethylene filter to filter out any optical light and let the terahertz light pass through, and then we just put the device in the beam. So there was no focusing optics used. And here also, basically the laser light was coupled to the fiber by overfilling. There was also no optical component used. Initially, they used actually a lens to couple the light into the fiber, but the laser beam drift was compared to the fiber diameter was such that there were too much intensity variations when a lens was used. Then we have here the frequency spectrum, also the Fourier transform here of the signal. We see we have like a dynamic range, which is basically like a factor of 10. We see signal maybe up to like maybe 1 terahertz, 900 gigahertz, and the dashed red line, this is the spectrum of the time domain terahertz radiation source. And here this a black solid line, this is the frequency response calculated for the device which we investigated, where the NZI arms were, this is a typo, 600 micrometer, where we had a fused silica substrate, and the optical index of refraction was 2.4. And we also took into account the dispersion of the 40 femtosecond laser pulse in the fiber. So we found a quite good agreement between the expected frequency response and the calculated, also the measured frequency response. Now here at the IVBT, we are looking at testing the sensor at very low intensities. We are basically at the other end of the electric field strength spectrum. Here we have approximately maybe 10 or a few tenths of volt per meter. We also work in a pump probe geometry. We use Menlo Systems C-fiber laser, which operates at 50-60 nanometer, which produces 90 femtosecond laser pulses at 62.5 megahertz repetition rate. And we use here scenario. The terahertz wave radiation source is a Menlo system photoconducting emitter. And we use this arrangement of 4 parabolical mirrors to focus here the radiation on the sensor, which is here in its sample holder, and the hole is on like an XYZ and rotary stage. Then for signal acquisition here, we use is basically the same like in Oak Ridge, only that we have that we use a lock-in amplifier. And for the lock-in amplifier, the terahertz pulse repetition rate is modulated at 30 gigahertz. And the ballast photodetector is identically actually with the one which was used in Oak-Ridge. And then the good news is we measure terahertz radiation pulses with the sensor. Although today in my presentation, I just show the results of the measurement. And you can see that this just happened, what is today, the 27th, 8 days ago. So there is no in-depth data analysis. We actually did vary some parameter. In this sense, we focused on setting up the experiments, which took us a couple of days, and finding the best arrangement. Then on searching for the signal, which also took us a couple of days. And then when we found the signal, we focused on optimizing the parameters for the lock-in detection, and then also the scanning speed. The scanning speed is basically then the optimized signal. But we see, we have a very low intensity in the terahertz radiation beam. So my estimate is 10, 20 microwatts, which produces like 10 volt per meter feeds. But we see here the terahertz radiation pulse. And here, this is the Fourier transform of this time domain trace, and the expected bandwidth of the device is 1.2 terahertz. So we do not really expect that we are sensitive for this specific device for higher frequencies. And this is basically also what we are seeing here in Fourier transform. This is the noise floor, and we have here almost 3 orders, if you go from here to here, 3 orders of magnitude dynamic range. We also see that the maximum here is around, this is 200, is 400 gigahertz. And so this is how the pulse looks like. We measured. So it works. We also then moved on to do measurements at IR2 here at Cara. So this is a step where an experiment where a measurement where the terahertz radiation source, which is basically the electron bunch circulating in the synchrotron, is really decoupled initially from the femtosecond laser probe. So we have here not a pump probe geometry where basically the same laser pulse is split, and then one pulse generates the terahertz radiation and the other one detects it. So this desynchronization is achieved basically by splitting the beam in this pump probe geometry. We don't think it not would happen here. We have the terahertz pulse repetition rate at 2.7 megahertz, which is the circulating frequency for the electron bunch. Then here the beam comes out of the beam pipe, out of the synchrotron. Then we have a large parabolic mirror which connects the radiation also with a long focal length, and then which focuses here again on the sensor, which was again, this is our very nice sample holder on the XYZ stage. Then we were probing it again with the Menlo System C fiber laser at the 1560 nanometer. This laser was synchronized to the Cara RF clock at 500 megahertz with the Menlo System Synchro box. And then we did time sweeps of the laser probe pulse of the Menlo system using the Menlo System DDS 120 distance. And the data acquisition was then the same. We had again the balanced photodetector, the lock-in amplifier, and we were visualizing the signal on the oscilloscope. For alignment, we determined the position to the best of our capabilities using the Schottky diode detector. And then we put here the sensor. This is the horn antenna of the Schottky diode detector. When we had the signal maximized here, we put the sensor really in front here of the antenna. And we also use the signal from the Schottky diode basically as a marker in time to find the signal. And then we actually found one. We found a signal. So this is a terahertz wave transient emitted by the synchrotron. So we see here we are here basically 30 picosecond. It's rather long event of also what we measure here with the trailing axis of almost 60 picosecond. And then we have here like a main cycle of around 20 to 25 picoseconds. So we just did this basically last Thursday. And here in this measurement, the laser pulse repetition rate is the 62.5 megahertz. The terahertz pulse repetition rate is the 2.7 megahertz. So only 1 out of 23 laser pulses actually detects the signal. Then we also did the Fourier transformation of this transient. So this is here the spectrum. You see that we have here the noise floor, and we see that the maximum of the signal is here. And what we see here is also that it kind of rather quickly decays. So this is a zoom from 0 to 700 gigahertz here of this part of the spectrum. And then we can see that the maximum here is at 100 gigahertz. But then basically within the next 100 gigahertz, the signal almost decays to the noise floor. So there's really a different characteristic. Here I have made a comparison. So we have here this is done with the Menlo system in the pump probe geometry. This is done here with at the beamline. And my expertise is with the sensor, and my expertise is with the terahertz waves with the sensor. I'm not an expert on the generation and the properties of terahertz waves generated in a synchrotron, but the spectra look different, and from my perspective, they are also which might be a property of the source. But as it concerns measuring the synchrotron terahertz waves, as from my point of view, the beam properties are really different. And here we have a point source. We have a parallel terahertz beam, which is then focused in the end by a mirror with a short focal length on a rather small spot. Whereas when we are here at the synchrotron beam line, the diameter of the beam is larger. It is likely also a kind of diverging beam which falls onto this parabolic mirror, which then produces a kind of weak focus on the where the detector is put. And then, as I said, I'm not expert on the terahertz waves produced by the bunches, so I do not know what the expected spectrum here is. But they look different. Okay, so I'm towards the end of my talk. So we designed and fabricated an integrated electro-optic electron beam sensor envisioned electron beam sensor in thin film lithium niobate. We have now successfully tested the sensor, detecting in a pump probe geometry low electric fields of low strength and low electric field of high strength. And we also have detected approaching electron beam diagnostics here by detecting a coherent synchrotrone radiation, which kind of requires this step of synchronizing the laser and the probe laser with the terahertz information. So if I come back to the talk of my presentation, the new perspectives, I think the new perspectives provided by a thin film lithium niobate it has a large electro-optical coefficient. It is like 10 times larger of a zinc telluride and almost like 30 times larger than gallium phosphide. So we can tremendously increase the bandwidth compared to bulk lithium niobate by using integrated optical waveguides, which allows really to minimize the mismatch in the propagation velocities compared to a bulk lithium niobate. And then there's also, since all the optical functionalities are integrated on a chip, there is much less complexity. There's much reduced size and much reduced weight. And since it is fiber coupled, it also eases alignment.
Okay, yes, for your attention.